So this project is for a class that's all about remote sensing, and the gist of it is we are building a four-man's LiDAR sensor using a camera and laser, and we're going to use the sensor to go out into the field on campus and map some object of our choosing on campus, and we produce a 3D model of it. I chose a fire hydrant. I think the size of a fire hydrant is a pretty good size. It's small, very scopable, easy to get around and manage. I like all the shapes and features of a fire hydrant. I think is nice and distinctive and interesting. And also because pretty much all fire hydrants are shaped the same way, I wasn't forced to just do that one fire hydrant in that one location. If I needed to, I would be able to scan any fire hydrants anywhere, which was very convenient. So that decision ended up being pretty important because the fire hydrant I originally selected was way too well lit at night. So this is the fire hydrant I was originally going to use, but way too well lit at night, and it's not nearly dark enough for the laser to pick up well. So instead I chose this one. Here at night, this one is pretty much in complete darkness. The closest lights are way over there and over there. So fundamentally the way LiDARs work is there's an emitter that emits some sort of radiation and a collector that receives it after it's bounced off of a target and comes back. Normally it's a laser and some sort of fancy photon detector, but in this case it's a laser, just a cheap laser pointer and a camera. The laser and the camera are positioned so that they are parallel to each other in the same direction, and this way the camera can judge the distance of the target by the horizontal position of the laser spot. This is my remote sensing apparatus. To make this as compact a package as possible and minimize the field hardware required, this is an all-in-one package that includes a monitor, so no laptop or SSH required. All you need is a keyboard, which plugs straight into the Pi. With the keyboard plugged in, just pop in an NPF battery and the system starts up. One connector on the battery powers the monitor, and the other connector powers the Raspberry Pi and the laser. This connection powers two voltage regulators, one of which runs the Raspberry Pi and the other is preceded by this switch, which powers the laser. The entire system mounts on this pair of rails, which is usually meant for camera rigs, but in this case it just serves as a very rigid and well-aligned mounting system. The parts that mount the camera and the laser to the rail system are machined on a mill to keep alignment as precise as possible. The Arduino is powered off of the Raspberry Pi, and its IMU is located here on this aluminum plate as flat and aligned as possible. Let's see if we can tell how far away the opposite wall of the room is. It seems, 16 feet. So I'm here at a slightly different fire hydrant than the one that I actually chose because it's kind of cold and wet outside, so I don't want to walk all the way across campus, but this one's pretty much the same. It even has the chain on it, so for the sake of this test, we're going to use this one. And we're here at night, so it's as dark as possible so that the laser is as bright as it can be in relation to the environment's ambience. The scan line that we're doing is right up the middle here from the bottom of the top, so should be that profile is what we should see in our plot. I'm going to try to scan just to the left of the chain so that we don't hit that and the laser doesn't get lost inside of it. To start collecting data, we just run the Python script, and then we get this window showing our reading. We turn on the laser here, and then just slowly pan up the object, making sure we get the whole thing, watching the monitor to make sure that it's collecting data at every point and backtracking if we have to make sure we get the whole thing. This position is working okay, but when we get too high, the tracking software starts to see those windows in the background, which are just too bright. It loses the dot in the bright windows. I think we've got to move the whole thing up higher so that that doesn't happen. We're losing a little bit of spots here, so I'm trying to go back and fill it in. It's pretty hard to get it to read on the green cap part, which is also a little more reflective, I think. Well, hopefully that worked. We're gonna have to go back to MATLAB to see if we got anything. The data could be better, but it's okay. The points are a little scattered, especially up here where the cap couldn't read anything, but overall, correlation is decent. It still wasn't perfectly dark, and I still had issues with getting the laser spot to be detected, so I ended up having to raise the detection threshold way up for it to pick up anything, which made it very sensitive to like windows back there. But I was able to remove all those false data points and get it to work. So here are the plots I got in MATLAB. And here's a side view, and the most important one, here's the 3D plot of all my points, which I was pretty happy with to see this. Looks pretty good. But when we bring that into MeshLab, this is what I got. The resemblance is not uncanny, but it's definitely a fire hydrant, and I'm happy with the amount of detail I was able to resolve. So if you ask me, I'd call that a win.